Basic Computation of Second-Order Derivatives. Hello, everyone. Let's begin our lesson on the basic computation of second-order derivatives. To start, let's look back at where we left off. In the previous subsection, we established the theoretical definition of second-order derivatives and familiarized ourselves with the various mathematical notations used to represent them. Now that we have the theoretical foundation in place, we will shift our focus to the practical application. In this subsection, we are going to learn the actual process of computation, specifically, how to calculate the second derivative of a given mathematical function. By the end of this session, you will be able to move from a starting function to its second derivative with confidence. Understanding the concept. Now that we have established the theoretical definitions in the previous slide, let's move on to understanding the actual process of computation. First, it is important to realize that finding a second-order derivative is a sequential operation. This means it follows a specific, step-by-step order. In essence, you are simply performing the act of differentiating a function twice. To put this into perspective, if you are given a function y equals f of x, the second derivative is simply the derivative of the first derivative. Mathematically, we can view this process in two distinct stages. In the first stage, you find the first derivative of y with respect to x, as you know from your previous lessons. This is denoted as di dx or f prime of x. Once you have obtained that result, you move to the second stage. Here, you treat the resulting expression, di dx, as if it were a completely new function and differentiate it again with respect to x. This final result is the second-order derivative, which we denote as d squared y over dx squared, or f double prime of x. Understanding this sequential flow is crucial, as we will see in the next slide how this applies to real-world physics, and later, how to calculate it using specific mathematical rules. Real-world analogy, kinematics. Now that we have established the sequential process of differentiating a function twice, you might be wondering why this operation is useful in practical terms. To help you visualize this, let us consider a real-world example from physics, the motion of a car. First, let us define the position of the car. We can represent the position at any given time, t, as a function denoted by s of t. Next, we consider velocity. In physics, velocity is defined as the rate of change of position with respect to time. In mathematical terms, this is the first derivative, which we can write as v of t equals the derivative of s with respect to t. Now, we move to acceleration. Acceleration is the rate of change of velocity with respect to time. Since velocity is already the first derivative of position, acceleration is the derivative of that derivative. This means acceleration is the second-order derivative of position, expressed as of t equals the derivative of v with respect to t, which is also the second derivative of s with respect to t. Therefore, whenever we calculate a second derivative, we are essentially finding the rate of change of the rate of change. With this conceptual foundation in place, we can now move on to the next slide and look at a step-by-step computation example. Step-by-step computation example. Now that we have established the theoretical definition and explored the real-world analogy of acceleration, let us move from theory to practice. We will demonstrate the computation process using a function that combines both a polynomial and a trigonometric function. Our specific problem is to find the second-order derivative of the function y equals x cubed plus tangent of x. As we discussed in the previous slides, finding a second-order derivative is a sequential operation. Therefore, our first objective in step 1 is to calculate the first derivative, denoted as di by dx. To achieve this, we apply the basic rules of differentiation to each individual term of the function. First, let's look at the term x cubed. By applying the power rule, where we bring the exponent down as a coefficient and subtract 1 from the power, the derivative of x cubed becomes 3x squared. Next, we address the trigonometric term. Based on standard differentiation rules, the derivative of tangent of x is secant squared of x. Therefore, by combining these two results, we determine that the first derivative, di by dx, is equal to 3x squared plus secant squared of x. With this first stage complete, we have a new expression that we can now use to find the second derivative in the next step. Step-by-step computation example continued. Now that we have successfully found the first derivative in the previous slide, let us proceed to step 2, which is calculating the second derivative, denoted as d squared y over dx squared. To do this, we take the expression we obtained in step 1, which was 3x squared plus secant squared x, and differentiate it once more with respect to x. Let us break this computation down into two parts to ensure accuracy. First, we look at the term 3x squared. By applying the power rule, we multiply the exponent 2 by the coefficient 3 to get 6, and reduce the power of x by 1. This gives us a result of 6x. Next, we move to the term secant squared x. This part is slightly more complex as it requires the use of the chain rule. To visualize this, let us temporarily replace secant x with a variable. This transforms the term into u squared. According to the chain rule, the derivative of u squared is 2u multiplied by the derivative of u. Since the derivative of secant x is secant x times tangent x, we substitute these values back into our expression. This gives us 2 times secant x, multiplied by secant x tangent x. When we simplify this by combining the secant terms, we get 2 secant squared x tangent x. Finally, we combine these two results to arrive at our final answer. The second-order derivative of the function is 6x plus 2 secant squared x tangent x. Please take a moment to review this process carefully, as the next slide will highlight some common mistakes students often make during this specific stage of computation. Common mistakes to avoid. Now that we have completed the step-by-step example, it is important to discuss some common pitfalls that students often encounter when computing second-order derivatives. First, let's address the issue of neglecting the chain rule. If you look back at the example we just solved, you will see that we had to differentiate secant x squared. A common mistake is to incorrectly differentiate this as simply 2 times secant x, or perhaps secant x squared times tangent x. This happens because the student forgets to multiply by the derivative of the inner function, which is secant x. My advice is to always carefully check if your first derivative contains any composite functions before you proceed to the second stage of differentiation. Next, we have notation confusion. It is very easy to confuse the mathematical symbol for the second derivative, written as d squared y over dx squared, with the first derivative squared, which is written as the quantity di over dx squared. Please be very careful here. The former represents the result of differentiating the function twice, while the latter is simply the first derivative multiplied by itself. These are two entirely different operations. Finally, avoid the temptation of skipping the first step. Some students attempt to jump directly to the second derivative in their heads without clearly writing out the first derivative on paper. This almost always leads to avoidable algebraic errors. To ensure your final answer is correct, always document your first derivative explicitly before moving on to the second. Key takeaways. To wrap up our lesson, let us review the key takeaways to ensure you have a solid grasp of the material. First, always remember that the second-order derivative is simply the derivative of the first derivative. In mathematical terms, the second derivative of y with respect to x is equal to the derivative with respect to x of the first derivative of y with respect to x. As we demonstrated in our step-by-step example, this is a strictly sequential process. You must start with your original function, calculate the first derivative, and then use that resulting expression to find the second derivative. It is also crucial to remember that all the standard differentiation rules you have already mastered, such as the power rule, product rule, quotient rule, and the chain rule, apply at every stage of the process. As we highlighted in the previous slide regarding common mistakes, be especially careful with the chain rule when differentiating the first derivative to reach the second. Finally, to keep the conceptual meaning in mind, recall the kinematics analogy we discussed earlier. In physical terms, if the first derivative represents the velocity of an object, then the second derivative represents its acceleration.